Okay, I wanted to give another perspective on why hydraulic jumps just go up. And it's a very short, very intuitive sort of reasoning that doesn't involve any of the equations I went through in the last one of these. And so, hydraulic jumps, another view. And it starts off by just a thought process. Let's say we have a fluid with a mean free surface that looks like that and no flow. And let's say we put just a little blip of a wave in there. You can think of this as a one-dimensional version of a pond. And you throw a stone into it. And it's a very shallow pond. But in time, part of this blip moves this way, and part of it moves this way. And I want to plot that down here. And I want to plot it in a funny way. X is that way, t is this way. So we put the blip here, and it partly moved this way, and it partly moved this way, and this is where v would be equal to 0. They'd be staying in the same place in time. And it turns out that this one moving to the right is at the wave speed, right? This is plus c. This one's at minus c. We have this wave speed. We have a formula for it. And so this is a plus c wave. This is minus c wave going that way. Now, I want to twist this. What I mean by twist this, I want to now add something to it. I want to say we've got the same configuration, kind of a uniform depth, but now I want v to be greater than 0, but less than c. So it's flowing to the right. We put our blip in, and after some time it moves to the right at speed v plus c, because there's flow in that direction and there's a wave moving in that direction. And it moves to the left at speed v minus, or c minus v, because it's trying to go at speed c, but it's going against the stream, and so it moves more slowly that way. So we can plot that here too. xt. We've got our blip here, and we've got kind of a center speed at speed v, and then we have a slope to the right, which is v plus c, and that's moving very fast. And we have slope to the left, which is moving more slowly in that direction. So it's twisted sort of to the right. Now I want to draw it for same configuration for v greater than c. So we've got our flow like this. V is greater than c. And so what happens now when we put a little blip in? Well, one of them moves fast that way. V plus c. It's moving more than twice the wave speed, because the velocity is the wave speed, and then on top of that, it's moving fast. And there's a second wave, and it's also moving to the right. This is v minus c. So it's trying to go to the left, but the flow is faster than the wave speed, so it's getting pulled backwards to the right. Backwards in the sense that it's against the way it wants to be propagating as a wave. And so we can plot this also in this sort of picture. So we've got our blip there. We've got the same set of sort of three characteristic velocities. You have a v plus c, you have a V minus C, and you have V, and they're all traveling to the right. Okay. Nothing is making it upstream. Upstream. It's totally unaware of the blip because look, no part of the blip travels in this direction. Okay, what does that have to do with a hydraulic jump? And so I'm going to just assume an initial distribution. Let's assume we have a flow that looks like this. And so it's kind of shallow and fast like that, and it's broad like this. So why do we expect this instead of what we had, or why don't we expect this instead of what we had last lecture? Which I've lost page one of somehow. We had this sharp kind of compressed, all this happens over this. We didn't use this dimension in our control volume at all. Why isn't this like a kilometer long? Why does it happen all in this range? Nothing about this analysis told us that. We just said, well, let's analyze this shape and it looks like this, but why is it short? Why does it happen on the scale of the depth? Why doesn't it happen on the scale of the entire river and we don't notice it at all? That's one of the main questions I wanted to answer in addition to giving you this extra perspective on this. And so let's say it happens over an expanded region here. And let's say the criteria are the same. There's nothing wrong with that last analysis. We know for it to go up, we need Froude number greater than 1, or V is greater than C in this region. We need Froude number less than 1. V is less than C in this region here. So let's consider 2 points right at the edge of this wave. And what do these travel speeds look like starting from these? Well, this one is in a region where V is faster than C, so it looks like this. We have something that looks like this, where we have a V minus C, V, and V plus C, but they're all tilting to the right. Nothing makes it here. And this point, it's still moving to the right, but there's some of this going on, and some of this going on. So that's supposed to be a little bit more symmetric, but it's functionally fine. V minus C, V, V plus C. And so look what has to happen here. Nothing makes it here either. Nothing makes it out in front of the wave faster than V plus C. Nothing makes it here. But look at this distance here. Let me use blue. I want to focus on the maximum distance between the start and the stop of the wave. So after some time, this is steeper than that, so it gets shorter. And then those points are like this. No matter what's going on in the wave, it gets shorter and shorter. And this is complicated by the fact that actually C is actually slower here. And so this is actually ends up being narrower than this one, and so this is actually more correct. The fact that this is narrower than this one, and so in time wave shortens. The region between where nothing can happen becomes no awareness of the wave can exist, becomes narrower and narrower. Now, the way this is crafted here, this whole thing is moving downstream and getting narrower and narrower and narrower downstream. That's the way that this particular one is set up. So that's why you get short waves. That's why you don't have your hydraulic jump being equal to the length of your river. I don't think that was in the analysis before. It's usually left out of these sorts of analyses. It also tells us what happens to the long jump. So the jump down can't exist energetically, but it also tends to broaden out. What if you created it? What would happen after that? So that would be this case. And so we're presupposing an initial profile that looks like this. The jump down profile. And here we have Froude number greater than 1, V is greater than C. And here we have Froude number less than 1, V is less than C. And again, I'm going to consider these 2 points right on the edge of the wave. And in this case, I'm going to show that they get further apart as time goes on. And I'm going to show it just to the same level that we've been showing everything here. And I'm going to just take these points and this point. And we know that the characteristics for this point are all going downstream. And so 1, 2, 3. And we know on this one we have 1 going upstream and 2 going downstream because this one's moving less than the wave speed. And you see we have the exact reverse happening of before. So if this is the length that started in time at time 0, look, now it's longer. And longer again. And so wave lengthens in time. And it's no longer a jump, and if it was something like it formed, you would never form a jump. It would get longer and longer and then eventually become a gradually flowing wave. Here, the characteristics are coming together. It gets narrower and narrower. And so even if we started off with this being some sort of wide thing, draw a control volume around it, we would expect that the mechanics of it, the wave speed and the flow speed, would be such that it narrows into a hydraulic jump eventually. And then once this starts to form, yeah, it's trying to form basically something of zero width, but that can't happen. Other mechanisms come into play, and that's why you get a finite but order 1 width hydraulic jump. And that's all I have to say about that.